Let's prove that every natural number, n bigger or equal to 2, has at least one prime divisor. This is a very first step towards the proof of what we call the fundamental theorem of arithmetic, which is the theorem that says that every natural number has a unique factorization as a product of prime numbers. We're going to use what we call strong or complete induction, and for that we start with our base case. N equals to 2 has a prime divisor, namely p equals 2. Now, to prove the induction step, we assume what we call the induction hypothesis. We suppose that the theorem is true for every number up to n, so that every number between 2 and n has a prime divisor. And now we consider n plus 1. There are two cases to consider. If n plus 1 is prime, then, well, p equals n plus 1 is a prime, and it's a divisor of n plus 1, so it has a prime divisor. Now, second case. So what if n plus 1 is not prime? By definition of prime, n plus 1 is composite, and therefore it has a non-trivial divisor, so some number between 2 and n, so smaller than n plus 1 and bigger than 1, that is a divisor of n plus 1. We don't know if it's a prime divisor, it's just a divisor. However, this number is between 2 and n, so by our induction hypothesis, the theorem is true in that range, so D itself has a prime divisor, namely, let's say, p. Then we know that n plus 1 is composite, it has a divisor, and that divisor has a prime divisor, so for some m and t other integers, and if I plug in d in there, then I get that n plus 1 is a prime times an integer. Therefore, by definition, p is a prime divisor of n plus 1, and hence by the principle of mathematical induction, the theorem is true for all n bigger or equal to 2. One final remark, that we need strong induction and not just simple induction, because if I only knew that n has a prime divisor, I would not be able to deduce that n plus 1 has a prime divisor. I really need all the numbers in that range, because d, the divisor, will be somewhere in there, but I don't know where, and it will not be n. So we definitely need to know the theorem for all the numbers up to n to be able to complete the induction step.